Thank you. Thank you for the invitation. Sadly, I won't be staying too long, but until tomorrow afternoon, I'm here. So the motivation for this is I guess for this audience at least, is joist structures. So this is, at least recently, the topic of isomonodromic deformation came up in the context of twistors through these joist structures associated to Donaldson-Thomas theory. And this morning, we saw a class of examples that were associated to this A2n. So these were quadratic differential with a kind of polynomial behavior on CP1. And the relevant moduli space was a moduli space of a curve, which in that case was just P1. And then you had a quadratic differential, and then a line bundle with connection. And this was this Tn. And you had a fibration over a base where you had just the moduli space of a curve, a quadratic differential, and this was your M. And it was identified with some space of stability condition. Now, in fact, the subject of isomonodromic deformations has a much longer history than this one is, since the early 1900s, when basically Fuchs realized in like the 1910s Painlevé equations as consistency conditions of differential equations. And the natural starting point is kind of a different moduli space, which is a moduli space. Again, you have a curve, you have a vector bundle with a connection, and what is called a Higgs field. Now, for this talk, well, essentially, a Higgs field is a matrix-valued one form on C, a meromorphic one form on C. And there is a map from this space to this space. The curve is the same. Then Q0 is just minus the determinant of phi. Here we are, this side here at least is in SL2. In general, this would be some Lie algebra valued matrix differential. So you take its determinant, because 2 by 2 is just a quadratic differential. But then, in the context of isomonodromic, the kind of more traditional approach is rather, the more traditional geometric context is a bit of a different one, where you have a curve, a vector bundle, and a connection. And this connection here is related through this map to the objects above in this way. And again, just essentially the map from here to here is the same. The line bundle with connection was discussed this morning. I won't go into that, because actually what I want to do is to stay here. And I want to, because this is such a, it's a subject with such a long history, I would try to provide a bit of a gentle introduction to the subject, and in particular to some very central functions, which are the isomonodromic tau functions. So essentially, this epsilon here, just if you want connection with what is was said today, this epsilon is the P1 parameter of the Twistor fibration. So here you have a vector bundle with a flat connection on a curve, and you have what is called the Riemann-Hilbert map. And this associated to the space, so you have some flat connection, you associate to it its monodromy. But because this is not just moduli space of flat connection on a fixed curve, this map is not an isomorphism. It has a big kernel, because there's infinite families of flat connections that have the same monodromies. And as a result, you have these isomonodromic flows that I'm going to describe. So this is kind of the geometric setting, kind of overarching geometric setting. And lately, in the past 10 years, the subject of isomonodromic deformations and tau functions has had a spectacular number of developments, which include very explicit formulas for the general solutions of these systems, which previously was thought to be impossible, and connections with a bunch of fields in mathematical physics that include string theory, conformal field theory, but also random surfaces, Hoyne equations, Teichmuller spaces, and so on. So, yeah.
Flat for a particular value of epsilon?
No, this is flat for all. Yeah.
Oh.
So in some sense, this epsilon here is kind of.
No, I understand.
Yeah.
Yes.
So, and the reason why I.
This is
yeah.
the Hitchin system. The Hitchin system
Yeah.
so
It's.
This is in the world of top equation stuff.
Yes. They're related by something that is called conformal limit. So the reason why is, so basically the gist of it is, if you're interested in joy structures, well, there's also an object called the tau function in the context of joy structures that is much less understood. In some cases, it's known that this object and that tau function coincide, but this we really understood on a deep, both analytic and geometric level. So kind of as an invitation, if this is what you want, this is what you're interested in, there's already a lot that we know about these objects. So let's so for ease of notation, I will denote this space here by A epsilon. So the Riemann-Hilbert map will be from A epsilon to M. So what are these isomonodromic deformations? So we saw today that you can represent them as some vector fields on Tm, but the traditional, the more standard way that one would obtain isomonodromic deformation is, well, you have this flat connection. Well, this you represented as some D minus A, and then the condition for this to be isomonodromic is that you take some solution, you go into some local coordinate, you take a solution of this is, in this case, we're in SL2, it's a 2 by 2 linear system on the curve C, and then you have a bunch of this matrix A in this local trivialization will depend also on a bunch of additional parameters, and some of them will be such that you can have another auxiliary linear system. So this is a function of x, but also the TIs, same here. And these two are compatible. So this is kind of the non-autonomous version of the Lax equation. So you have just the compatibility conditions here are these isomonodromic deformation equation. And if you go into some specific set of coordinates, like these z and theta's that also are parameters on this space A, you can represent these flows in, for example, as this Lebansky heavenly equation. But in general, if you're given some flat connection, you would obtain kind of very directly these isomonodromic flows just by considering compatibility conditions here. Now the immediate question is, what are these parameters Ti's? Because this A will depend, like you can parameterize it in some crazy ways, but actually that's, there's a very systematic way of understanding what these Ti's are. So there are basically two types of times that you can consider. And one is what are called regular times. And what regular times are the positions of the simple poles of this A, plus all the Teichmuller moduli of the base curve. So, for example, if you have A of x is equal to some A0 of x plus A1 of x minus 1 AT over x minus t, then you have one time, and it's the position of this fourth pole where I fix the others by SL2C. If I was on a, for example, over an elliptic curve, I would have the elliptic modulus of the base curve in addition to the positions of the poles. And then we have the irregular times. That are not related to the geometry of the base curve, but are really some more complicated. They're contained in this A, or rather in the Higgs field, in a bit more complicated way. But you can still write them like fully. So for example, so let's say that the spectrums or the eigenvalues of this of phi are given by YA of x. So in the case of SL2, this would be just y minus y, but in general, you will have a bunch of eigenvalues. And then you have P jk of A. You construct all these. Actually, you know what? Let me just stay with SL2 just to have simple formulas. You consider, as today in Tim's talk, the canonical differential, and then these irregular times are just minus the residues at all the punctures, so they're labeled by two integers, of x minus xk to the j y dx. So you're just considering the local behavior of this meromorphic differential, and you're taking the polar part, basically. And these are dual in the sense that you have this, you have a Higgs field, which is a matrix-valued one form, and you can define a Poisson-Lie bracket from loop SL2 or loop SLN in general. So this would be kind of conjugated spectral parameters with respect to that Poisson bracket. And these are the Hamiltonian this is the Hamiltonian generated this time flows. So all these time flows are given by some Hamiltonian vector field with respect to this Poisson bracket, are generated by some Hamiltonian with respect to this Poisson bracket, and which are these. And also these have this very kind of analogous definition. So this was already studied by Jimbo Miwa-Ueno in the 80s, but kind of in the most general case, I'm using the notation of Bertola, Harnad, Hurtubise, 2022 or 2023. Let's say the preprint should be from 2022. I don't remember when is the published version. So actually, this formula looks very cumbersome, but it's just telling you something that is actually rather nice. That if you consider, so you have these regular times. These regular times are given by the Teichmüller moduli of the base curve, so with mark points. And then these irregular times are just local information around the higher order poles of this A. And you can immediately, if you expand the canonical differential around the higher order pole, you can just immediately read off what are the times and what are the Hamiltonians in terms of however you're parametrizing this thing, because this will be ... And then let's write T2k over cube plus T1k and then you would have just called the local squared local monodromy exponent. And then here you have the simple pole, which is what is telling you what is the formal monodromy around that point. And then kind of the times and Hamiltonian are distributed in this mirror way. So the immediate leading part with respect to this is the first irregular time, which is whose isomonodromic flows is generating by this first irregular Hamiltonian, and so on and so forth. So it's actually quite easy to read off. And instead, the regular Hamiltonians, well, the ones that are related to the movable poles, so just moving xk while keeping fixed the monodromies, are just the Schlesinger Hamiltonian. And then you have some more involved formula for the other regular Hamiltonians that involves defining some Beltrami differentials. But the point is, all these Hamiltonians actually Poisson commute. So hi, hj is 0. And because of this, the compatibility of these flows only require, in terms of the Hamiltonian, that the mixed times derivative are equal. So this means that there must exist, at least locally, a generating function for these Hamiltonians. So this gives us our kind of definition 0 of what is an isomonodromic tau function. The isomonodromic tau function is such that its logarithmic time derivative with respect to the times give you the Hamiltonian. So it's the generating function for these Hamiltonians. Now, this is not, I mean, this is okay, working definition. But it has at least a couple of issues. One issue is that it depends on a choice of times and Hamiltonians. So if I do some Poisson transformation on the Hamiltonian, I will get some different Hamiltonians, and then I will get some different representation of these flows. But it's not clear. I mean, this tau function will transform in some complicated manner. So this is not very invariant. So one, yeah. Mm-hmm.
What was lambda then? Sorry.
So yeah, lambda is this y dx.
Oh, it's y dx.
Yeah. There is also kind of analogous formula for arbitrary Lie algebra, but in this case we're in SL2, so there's only y dx. Are there more questions?
Sorry.
Yeah.
So you've got a little y dx, you've got a capital Y, which is the solution to the
Yeah.
system.
Yeah. Yeah.
So the little y, you diagonalize phi.
Yeah.
And then little y is the eigenvalue
Yeah.
capital Y under the diagonalization of the capital phi.
Yeah.
And capital phi was somewhere in your lax system. Somewhere.
Yeah. So this A is some reference connection. So this, yeah, maybe I've been. So yeah, sorry for that. I'm thinking of this A as given by some reference connection plus 1 over epsilon phi. Yeah.
And also phi defined the quadratic differential.
Yeah. 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 Yes.
And so then you also have a little y squared equals quadratic differential.
Yeah. Yeah. So
and lambda's the integral of y. No,
lambda is y dx.
Oh, it is just y dx.
Yeah.
But there's no wall index on the right side.
Oh yeah, yeah. Sorry. Well, that will be y. Sorry, not lambda.
Oh, that's fine.
Yeah.
Okay.
Well, if I multiply by the x. Anyway, it's just a local expansion.
Yeah.
So, no, of course. More questions? So just to, since the quadratic differential came up, today what we had, so the way that one gets the picture with quadratic differential is just very kind of simple writing this. This is a 2x2 first order system of linear ODEs. And you write it as a second order scalar ODE. And then if you do it, you will get something which is minus, and then you get Q0 epsilon squared minus Q1 over epsilon minus Q2. And then let's say Y11. This is just the 1 entry of that matrix Y. And this is the quadratic differential that was kind of forming the base of this vibration today. And this is what is used to define this line bundle. So this is the connection between the two pictures. It's just kind of passing from a 2x2 linear system of ODE, first order, to a scalar second order. That's, of course, this should be done in a more invariant way if you're not over P1. Involves going from a flat connection to an OPER, and then your group goes from SL2 to PSL2, but let's sweep these things under the rug. So, as I was saying, this definition 0 of tau function has kind of two main problems. One is, let's say, not canonical, not invariant. Well, depends on a choice. And two, you see here, everything in the end, let's keep this picture of A, M, Riemann-Hilbert. So through the Riemann-Hilbert map, everything will depend on this time parameter and the monodromy, nothing else. And this only fixes the dependence with respect to the time. So this is defined up to arbitrary function of all the monodromies. So if I just multiply tau by any function that depends only on the monodromy, that's the same. It's kind of ambiguous. Now this first issue was kind of fixed almost immediately by at least for linear system for flat connection on P1, regular or irregular, by Jimbo, Miwe, Ueno, still in the 80s. But the way that I'm gonna write things is a bit of a more modern rewriting of the same thing. From Itzlis, and Prokhorov. And the point is that, let's say that you have this linear system, the coefficients, the matrix A has a bunch of singularities. And then there's Y around the singularity K, xk, will have a formal solution, which will be some asymptotic series, regular asymptotic series around xk, and then some exponential behavior if you have an irregular singularity. And this you can just immediately just completely determine through the equation. And as it turns out, this definition of tau function is equivalent to the following. Let's combine all these derivatives with respect to the times into kind of a exterior differential on the space of times. So, and then this dt log tau is given by a one form on the space of times. What is the space of times depends on what is the problem that we're considering. Like if we have only simple poles, then it's a Teichmüller space. And this we can write directly just in terms of A, or rather of this GK. This will be the residue, the sum for all the singularity. This is, again, for the case of P1, linear system over the Riemann sphere. So you have the residue at xk, trace of gk of x, gk of x inverse. So this is kind of a covariant way of rewriting that formula through what is called the Jimbo-Miwa-Ueno one form. And if you go, if you start defining the Hamiltonian, this will be just sum of hi dti, which is just telling you that. So this was kind of already built in the original constructions of the 80s, but it contained in itself kind of the germs that led to the solution also of the second problem. And we'll see that this tau function has actually very deep geometric meaning. Because, so it was observed, well, it was proven by Malgrange that this, well, one can observe that this Jimbo-Miwa-Ueno one form has poles in T at the point, so at the point so this omega GMU will depend on all your times, all your monodromies. And it has simple poles with residue 1, where this times a monodromy corresponds to a non-trivial bundle over P1. So what happens is that this has a pole when the Riemann-Hilbert problem associated to that linear system is not solvable. And this means, just because this tau function is the logarithmic derivative, that the tau function will have zeros when RHP is not solvable. So this is a regular function, doesn't have poles, it only has simple zeros. And these simple zeros determine a divisor in the space of monodromies times, which is called the Malgrange divisor. So if you want, you could define the tau function as exactly the object that has simple zeros on the Malgrange divisor, and it's regular everywhere else on the space T times M. And this tells us, gives us kind of some indication on how to extend the definition of the, because now we're really considering the tau function as a function of everything. So this definition of the tau function was used by Bertola to kind of propose how to give a definition of the tau function that included the monodromies. But now comes the non-trivial bit, that you can define it this way. It's not very concrete. It's I mean, it's a kind of a very abstract, highbrow geometric definition. But in practice, if you want to write an equation like the Jimbo-Miwa-Ueno one, the one that Jimbo-Miwa and Ueno wrote, you would like to write something like d log tau is equal to some one form on T times M. So the immediate guess for this would be just to take this and replace this dt by dt plus dm. So exterior differential over all your space. So you would have all this sum, residue, etc., dgk, gk inverse. But this is not closed. So this definition is inconsistent. But as it turns out, so let's call this omega A. As it turns out, we have that d omega A is a two-form of M, only on M. Does not have any component along the t's. And furthermore, it is time independent, so its coefficients do not depend on the t. So we just have to kind of correct this formula by subtracting something. So let's call this omega. Subtracting another generating function for the same omega. But this is time dependent, has components along everything. This is just on M. And you might say, okay, well, fine. But this actually leads to a very nice geometric interpretation of the tau function, because let's go back here. Here you have a moduli space of flat connection. Here you have the monodromy space. These are both symplectic varieties. There's the Atiyah-Bott symplectic form here, and there's the Goldman symplectic form here. And in fact, this omega A is, well, in this case, we're on P1. Yeah, well, it's the reduction of the Atiyah-Bott symplectic form modulo gauge transformation. So for example, for simple pole, it would be called the Kirillov constant symplectic structure. And d omega m is, well, the symplectic form on monodromies pulled back by the Riemann-Hilbert map. And the fact that this form is closed is because this is a symplectomorphism. And this was proven by many, many people, like for regular singularities, Alexeyev-Malkin, Hitchin, Korotkin, then for the regular case, already Flash-Canuel, Ugalia, Bolch, recently Chekhov, Mazzocco, and Rubstov. Many, many people studied the symplectic aspects of this map. But now we have this, at least for connection on P1, we arrive to this definition that the tau function is, in this case, the generating function in the sense of symplectic geometry of the Riemann-Hilbert map. Because it's a difference of two symplectic potentials, one here, one here. So it's really the generating function of this map. And now, in all this isomonodromic literature, typically one works at epsilon equals to 1. So if you want to study, so all these formulas for the tau function have always epsilon equals to 1, because again, it's kind of a formal parameter from this point of view, at least. It's a formal parameter that it seems put a bit by hand if you don't understand already that it carries this twistorial construction with it. And it parameterizes the Twistor fibers. So one possible way to study the epsilon dependence is through WKB approximation. So you take this generating function, and then you study what these formulas look like order by order in H bar. And for example, so this is what we did with Bertola and Korotkin. And it turns out that its various terms in the WKB expansion have also some nice geometric interpretations. They're related to the Berman tau functions, and they're related to generating functions, homological coordinates. There's a lot of story there also. So this you can do also for, so the analytic part of the story is in this paper by Itzli, Sovi, and Prokhorov in Duke. And then this interpretation as generating function it was developed for a Fuchsian system, so SLN Fuchsian system on the sphere. Fuchsian means simple poles, by Bertola and Korotkin. And for Fuchsian system on elliptic curves, so Fuchsian on P1, Bertola, Korotkin on the torus, where you have to be careful because then you start to have the existence of non-trivial bundles over the base curve, over the non-punctured base curve. And so there are additional moduli to take care of. This is something that we worked out with Areni Desiraju and Pasha Gavrilenko. So this is kind of the geometric picture of what a tau function is. You start from kind of this elementary classical mechanics point of view. You have all these commuting Hamiltonians. This means you must have a generating function. And then you see, oh, actually, this defines these divisors on the moduli space of flat connection, bundles with connection on P1. And then you actually see that this object carries a lot of information about the symplectic geometry of these spaces. So in the last part of my talk, I want to give some idea about, I guess, two analytics. Because a lot of the recent progress on understanding these objects comes from the fact that we can really study them in full analytic detail now. So it was kind of common lore until 2010-ish that you would hear a lot of people just say, no, Painlevé equations, they're too transcendental. Painlevé equations are kind of the basic examples of these isomonodromic deformations. It would be like, yeah, Painlevé equations are too transcendentals. We can study with Riemann-Hilbert problems. You have very powerful techniques to study their asymptotics in many different regimes. You can get a lot of information about their solution, but you will never be able to write the general solution to a Painlevé equation in full detail. Then again, it depends what you mean by full detail, because if by full detail you mean can you write it in a simple enough expression that involves only classical special functions, then the answer is no. That's kind of the definition of a Painlevé transcendent. It's too transcendental. But now we know. So in 2012, there was this paper by Gamayun, Yorgov, and Lissovi. It was a physics paper into two-dimensional conformal field theory. And they derived this formula for the tau function of Painlevé 6, which is now known as the Kiev formula. And this is telling you that the tau function, you can write it in this form. I'll explain the notation in a moment. So this is an expansion over couples of color partitions. This is just an integer, and this is in Z. Nu and A are initial conditions for Painlevé 6. And this is, they're called Nekrasov functions, or Virasoro conformal blocks. But the point is that these are just some expressions that you can write down for any partition. And now it has also been proven that this is a convergent series. So if by explicit you mean we have a convergent series expansion with all the coefficients written in closed form, we can describe the general solution in very explicit detail. Oh, they're really like, so you pick a partition. Yeah, sorry, this Y is a partition now, but
Oh, the Y.
yeah,
sorry.
yeah.
Yeah, no, it's okay.
Yeah, so these are just, for SL2 case, you would have 2 partitions. For SLN, you would have n partitions. This is charged, so you can write it in terms of Maya diagram if you ever saw that notation. But the point is that this is kind of just a rational function that you write in terms of hook and arm length of these partitions. It's just something like.
And to go from the, you explained it, but to go from the actual solution of Painlevé 6, that's one writes it equation, and this tau function, that's some limit. You don't have to. What do you have to do? If
Well,
you give me a tau function, I want to find y.
All
of x.
for all Painlevé equations, the solution is the second logarithmic derivative. So then here, like for example, for Painlevé 6, maybe it's like a t minus 1 d in dt, but
Okay, so then I was going to, so Painlevé 6 has these 4 parameters.
yeah, so these are here. These are, here you have all the parameters. Theta 1, well, all the, so this would be the, what I was calling, well, before, these exponents of formal monodromies, and they're here.
So there is this confluence.
Yeah.
Limits.
Yeah.
You know, at the end of all these limits, there is Painlevé 1,
Yeah.
which doesn't have any parameters.
Yeah.
So is there, can you do that at the level of this formula?
Yes.
And
So actually, it's so Painlevé 5. Then we have, it's called 3-1, 3-3, sorry, 3-2, 3-3, and then here you have 4. It's a bit more like there are more arrows, but no, sorry, it's yeah. So this is
What name was associated with this formula?
just this formula.
No,
So the article, the original article is Gamayun Yorgov Lisavi, but this is called the Kiev formula because
found in Kiev.
no, but every person that was involved in the early stages of these developments was Ukrainian and was from Kiev, at least.
so this is, and T is what you, okay. T is what U depends on. So you're expanding in T.
Yeah.
If you do it for Painlevé 1, you will be expanding in T around
Infinity.
infinity.
You typically expand around a critical point of the equation.
But infinity is irregular singularity.
Yeah,
So
so
it has some Thome index.
you have to specify a Stokes direction when you do it for those cases. but okay, so this is for Painlevé-6. For Painlevé-6, there's no ambiguity in this sense. Now we have actually a bit of a better description, which is that this tau function is a Fredholm determinant of well, let's see how much time I have. Okay, maybe I can give at least some idea. So you can write this tau function as a Fredholm determinant, so an operator kernel that is acting on L2 spaces over your base curve. And this, for Fuchsian system on the sphere, was done by Gavrilenko-Lissový. On the torus by a different paper by
The whole
me and
was a determinant or just the Z?
Sorry, can you repeat the question?
The whole is
Yeah.
determinant.
Yeah, it's this
Not
infinite.
just the Z.
Yeah. And this formula here comes from minor expanding this infinite dimensional determinant. So this would be kind of an infinite matrix with 2 by 2 blocks. So when you select your minors, you have to specify 2 partitions and then a charge.
And the K wouldn't happen to be sort of made of things like, well, P3 Bessel kernels.
Actually, that's the nice thing. So here you have hypergeometric, and then you have all your nice. This lower part is much more complicated. So this description of Fredholm determinant is nice for the upper part, and it's been fully developed for the upper part, and for Fuchsian singularities on elliptic curves. But this lower part only for Painlevé-2 by Desirajo. But it's much more complicated, and you don't have these closed formulas, essentially because your Riemann-Hilbert problem is over an open contour. Well, if you think about the Riemann-Hilbert problem for something like this, you have all these Stokes directions emanating from a singularity. And here, you can modify your Riemann-Hilbert problem so that it goes over a closed curve. But here, you can't. So just to give you an idea of what it means to modify the Riemann-Hilbert problem. So like, how does one get these Fredholm determinants? Let's just say that I have a sphere with 4 Fuchsian singularities, 0, t, 1, and infinity. So actually, I'll need a full blackboard for this. So the other nice thing is that because these determinants are fully analytic expressions, if you want, for example, to find the one form for problems on elliptic curves, well, that expression was not available in the literature, but once you have this determinant, you just take partial derivative. And that automatically gives you a closed form because it's a function. And partial derivatives commute. So let's say that you have these Fuchsian singularities on a sphere. So this goes up to infinity. So your Riemann-Hilbert problem would be that you have here the constant jump with monodromy around 0, here monodromy around 0 and t, monodromy around 0, t, m1. And here you have your function y, which was the solution of that linear system. Here it would be actually the solution to the Riemann-Hilbert problem, but let's gloss over this. So the point is that this is transcendental problem. So you won't be able to write this in any nice way. But what you can do is, well, first let's modify this by considering a different Riemann-Hilbert problem where I consider circles. So here I have solution at 0, at t. So I have different regions with where the solution of the Riemann-Hilbert problem is the local solution around that singularity. Here I have that global solution there that I can't find. But these are just some local expressions. And now the jumps are not constant. And now the kind of the very nice trick of Gavrilenko and Lissovy was that you observe that here I can split this as follows. The jumps here and here must cancel because there was no jump there. But now this, the solution here, is a solution of a 3-point problem. So let's call it y in, y out. 3-point problem with singularities here and a combination of these two. And the other one here. And now I confine my y here. So geometrically, this amounts to the following. I have a 4-point sphere, and I do a Pan's decomposition. But now the nice thing is that everything, I don't have time anymore, so if you want to know more, I'll be happy to discuss. But everything is now written in terms of operator acting on the circle where you're doing the Pan's decomposition. So if you had an irregular singularity, it would be something like Pan's decomposition with cusps. So this is a possible thing that happens for one of the Pain-Levé equations. So you have still this circle here, and you have these blocks. The lower one is a trinion and is given by hypergeometric. The upper one, this would be Bessel, I think. So you're kind of decomposing your transcendental problem into chunks that are known special functions, and you combine them in operator kernels acting on, in this case, circles. And the problem for the lower part is that instead you need operator kernels acting on lines, on infinite lines. And just to give a very brief concluding idea of what is this kernel here, the idea is that you consider two projection operator. Here you have two projectors. You have the Hilbert space of function here on this circle. So let's call this L2 of this S1H. And then I can consider, and I just do a Fourier decomposition into positive and negative frequencies. And then I have a projector from the positive frequencies to the functions to the space of functions that can be analytically continued inside the trinion. And then I also have, and this is just defined in terms of this. Yes, the boundary behavior is fixed by the monodromy around this circle. And
when you say extend,
and like by analytic continuation, that in the sense that it is possible to have this splitting. And I project from.
there's no conditional result.
Yes, so these are the things. So here you have the condition is that the local behavior is given by the local behavior of the original linear system. And then, so this is defined in terms of these 3-point solutions. And then you have a projector that is just in terms. So this is this. Okay, maybe I shouldn't have. So this is just defined in terms of y. This is just defined in terms of your 3-point solution. This is the projection on this space along H minus. And this is the projection on this space along the space of functions that are analytic inside this annulus. And this tau function is the determinant of P sigma plus inverse P plus plus. So this is this 1 minus k. And the point is that this P sigma is invertible outside the Malgrange divisor. So so essentially the point is this projection along H minus and the projection along HA are the same if this Riemann-Hilbert problem makes sense. And this Riemann-Hilbert problem doesn't make sense exactly on the Malgrange divisor. So this P sigma will not be invertible, and this tau function will become a 0. The determinant will become a 0. And then you can, if this is the general idea, but then you can compute its derivatives and prove that it satisfies all your definitions that you want about the tau function. So this is kind of, there are kind of very explicit formulas that you can touch. If you want, I can show them to you in more detail, but I think this is a good point to stop.
Question? This is equivalent to the formula that show that with some of our conformal blocks.
Mm-hmm. So if you want to think of it in terms of conformal blocks, what happens is that this is essentially, so a conformal block, you can think of it as a 4-point correlation function. So if I use Dirac's notation, here I have some state at infinity, which is parameterized by a monodromy at infinity. And here I will have some vertex operator insertion. And the vertex operators are defined by the local monodromies at your singular points. And that formula there is, I take this and I insert an identity, V1. And then the point is that the descendant state of Virasoro will be labeled by the highest weight. From the point of view of Virasoro, the local monodromies are the highest weights, essentially. So you have the highest weight, and then you can think of it in terms of free fermions if you want, if you're more inclined. Those are more used in the context of integrable hierarchies. But basically, that formula is insert the identity inside this.
Right, so you get some over different weights.
Yeah.
And that's equivalent to summing over the monodromies of this virtual cycle, right? So you're inserting.
The monodromy is fixed. So you
in the middle, the one that you insert also has a monodromy.
Yes. So, but the monodromy around here is just the monodromy. So the monodromy around C is the product of the monodromy at 0 and the monodromy at 1. This is just a circle. So this is, sorry, INT. Because yeah.
Probably completely wrong, but in the old paper by Seligman, there was, you know, this, I mean, the Tor function, if I remember correctly, Tor function, you have the determinant light model of the Rossmannian, and the Tor function measures some distortion of the section when you act by the Beanian group that's giving you the flows of KP.
Yeah.
Is there, I mean, is there a similar interpretation?
You can write, for the case of the sphere, you can write this. Yeah. So if you go to more of a Sato kind of way of thinking, and you write everything in terms of fermions, you can see, and actually we do have this in a more or less explicit way in this paper with Bertola and Harnad, where we do discuss a bit more these aspects. But in essentially, so the point is that what is here is your point, sorry, what is here contains the evolution, the time evolution, and what is here is your point in the Grassmannian. But these are not abelian flows. So that's why kind of these isomonodromic deformations get so complicated, because they're highly nonlinear. They're not exponential of some.
So maybe it's more difficult from the Riemann surface. I mean, you're moving T around.
Yeah. So
doing in a Riemann mapping.
Yeah, for the regular times, yes. For the
For the irregular ones, you're doing some group action.
And then the mapping class group will be symmetries of your equations. So you have some differential equations, so you're strictly speaking in Teichmüller space, but then you actually have symmetries that implement the mapping class group transformations. So for example, here you could study the behavior of the tau function at the origin and at 1, let's say, and the ratio of the asymptotics between the two is called the connection constant. And this was like a long-standing conjecture in Pan-Levé theory. What is this connection constant? Because the original definition that only involved the time could not determine it. But now this has been derived for Pan-Levé 6, for Pan-Levé 2. We are about to finishing a paper with Desiraju and Gavrilenko where we do this connection constant on the torus for modular transformation. So you go from tau to -1 over tau, and the tau function will have, where tau is the elliptic modulus. You do a S transformation in SL to Z, and this will also give you some representation of the mapping class group on the tau functions.
And then when you have an irregular singularity, you can think of that as more like the Siegel-Wilson loop group action at the singularity.
If you're on the sphere, yes. Sometimes. Yeah, because yeah, I would say yes. In general, yes. But for example, viewing the Riemann-Hilbert problem from the point of view of loop groups, for the lower part, it's kind of hopeless, I think, because for the upper part, you're going always on a circle. So you have a Riemann-Hilbert problem on a circle, and you have your jumps over the Riemann-Hilbert problem are functions from a matrix function on this circle. But as I was saying before, part of the complication with the lower part of the confluence, is that you have Riemann-Hilbert problem over open contours. So your jumps are kind of functions on infinite lines or half lines.
Right, just for the matrix K, I mean, there are two different ways I've seen these, see depth 1 minus K occurring in these cases.
Yeah.
And I think when you write down rational solutions, for example, I think the K's often the entries of K are the solutions to the corresponding linear equation, like the hypergeometric for P6 or the vessel for P3. But then there are more fancy things where the entries of K are actually integrals of.
No,
they're integrals of some function against pairs of vessel functions.
Yeah. Well.
So I was just wondering what the nature of the K was.
Here, the nice thing is that it's for the general solution, and the entries are the solution of these 3-point problems. Right. So, for example, here it's a 2x2 matrix kernel. It's not a scalar kernel. And here there will be something like 1 minus y in of z. Y in is the 3-point, so hypergeometric function, solution of a 3-point linear system in 0, t, and infinity. over Z minus W, and here you will have in, out, and so on.
Okay, so this might be the time to